This chapter revolves around the idea on Lebesgue's measure. But before we proceed to that, let's talk about the important ideal properties for a certain set M, which is what we will denote later on as Lebesgue's measure, to become really a measure. Now, the collection of Lebesgue's measurable sets, as we discussed in the previous video, is a sigma algebra. And it should also contain all open and closed sets. We're also going to talk about open and closed sets in this playlist as well. In the previous video, we talked about the definition of a measure function. Hence, those two are also very applicable when we talk about Lebesgue's measure. But this case, since we are going to talk about one important measure in real analysis which has great implications in further studies of measure theory, let us talk about what are the ideal properties for a certain set to be called a Lebesgue measure. The first ideal property, okay, is that for that set M, okay, we will talk about set function M. M here should correspond to the Lebesgue measure. Okay, this M should have this property of the mapping of your power set of the set of real numbers with mapping to this interval 0 to positive infinity. Of course, as mentioned to the previous video, measure function, we consider this as part of the definition, which means, or that is, okay, M is defined for all subsets of R. Okay, that should be what the first ideal property that our Lebesgue measure, or in this case M, again what we will denote to Lebesgue measure later, should be defined in all subsets of the set of real numbers. As this is the power set of the set of real numbers, it's a set containing all the subsets, right? So this M should be defined in all subsets of the set of real numbers. If there is one subset, let's say commonly we have the nice set of negative numbers or set of irrational numbers or set of fractions, and if that set M is not defined in any of those, then definitely M is not a measure or a Lebesgue measure in this case. This should be the first ideal property. The second property is this: for M of a certain interval, for this, since M is a function, just like f of x, yeah, f is a function, so f of x, we know that commonly on our algebra and other advanced algebra topics. In this case, M is a function. I here is any interval, is just equal to the length of the said interval. Okay, this should be true for every interval I. If you were not able to remember this, take note that the length or the length function of an interval, say for example, if we have the interval A and B, this is our interval, okay, I, okay, so this means this is our I. Our length of that set interval, okay, the length function is just B minus A. Just like if we have the interval, okay, just illustration, 1 to 7, the length of this interval, the length of 1 and 7 is 7 minus 1, 6. This should also be equivalent to the M of your interval here, or M of your interval 1 and 7. Because this is the ideal property stated here. Okay? So this should also be true for the Lebesgue measure. That's the second ideal property if we are trying to look for possibility of existence of Lebesgue measure. The third, let me move it down here. The third property, of course, this is not important if any of the first two is not satisfied. But in this case, if the first two is satisfied, the measure should be translation invariant. Okay, measure is translation invariant. The term translation invariant means that if we are going to translate our interval, so say for example, if we are to add a certain component to our interval, the measure should, or measure in this case in our second ideal property, the length should not be what they call this one, should not change its value. It should retain its value. This is its complete term here. If a certain E, let's say it's a set, okay, is Lebesgue measurable, and Y, sorry, that's and, my bad. It should be and Y is, let's say, any number. Okay, this is what we mean by translation invariant. Then the translate of E, okay, by Y. As mentioned, we're going to have here, say for example, the measure of E plus Y is just equal to the measure of E, or again, the length of E. In this case, if it's interval, right? But we're not sure if E is interval. It should be equal to that for all E subset of the set of real numbers. Okay? Where E plus Y is the set of X plus Y for all X element of E. Which means that if we have here this expression where we add Y to all X's in E, is the measure of that is just equal to the measure of E. That's why it's called translation invariant. It doesn't change its value when we translate the measure. Let's just say, for example, E is an interval here. Let's say it's an interval, open interval, 1 to 9. And let's say Y is equal to 4. We know that the measure of E, as mentioned in the second property, is just equal to the length of the interval 1 and 9, which is equal to 9 minus 1, it's 8, right? What if we have E plus Y? That would mean we're going to add 4 to all the elements in our interval E, which is 1 and 9. That would mean 1 is no longer the lower bound, plus 4. Okay, you will have here 5, and then your 9 becomes 13. Because that means we're adding all. It can look like this if you would like to. 1 plus 4 and then 9 plus 4. Of course, all the entries between them are added by 4 because that's what we have here. So this is actually, again, as mentioned, 5 and 13. If you're going to take the measure of E plus Y, where Y is again 4, it's again equal to the length of the interval now identified as 5 and 13. And we know that the length function is just the difference of the upper bound minus the lower bound. We will still get here 8. We can see that the measure of your E in this example is equal to 8. Here it is. It's just equal to the measure of E plus Y. This is what we mean by translation invariant. Because however you translate, in this case interval, you will still have, using the same value for all elements of that interval, or if you talk about interval, it's a subset of the real numbers, they will have the same value. Okay, so I'm using here interval because I cannot yet present to you some examples of measures. We will have it later, some few examples. I presented this interval because since it's connected to the ideal property number 2, so we'll have that. Okay, and the last here, hopefully my space is enough. For the last ideal property, this, again, 4 properties should be considered for us to say that M is a Lebesgue measure or Lebesgue measurable. 4 here is measure is countably additive over, sorry for that, let me rewrite it carefully, over countable disjoint union of sets. Okay? So actually, this is related to the second property of measure function, where we talk about disjoint collection of sets. Okay? Or in this form, it is actually uncountably additive, or what do you call this one? Countable disjoint. So we are not talking only for a certain finite set, but for which includes countable sets. So we'll have this form here. if set A sub I where I is a natural number is a countable collection of pairwise disjoint subsets of R, then this expression was already presented in the measure function in the previous video. The M, that's a function of all the union, countable union of your A sub I where I starts from 1 to infinity is just equal to the summation of the measure of each M sub I where I starts from 1 to infinity. So this tells us that if we're going to take the measure of all union, making sure that the collection of pairwise disjoint, meaning there are no common elements to any of those sets, okay, the measure of the union of that is just equal to the summation of the individual measure of each set, which I again consider to be pairwise disjoint subsets. Pardon for my handwriting because I don't have much space. So these are the four ideal properties for us to say that our given set function M, as we are using here, small letter M, is a Lebesgue measure, or just like that, Lebesgue measure, or it's a collection, set function of the collection. Okay, so these are the ideal properties which will be used later on our future discussions. Thank you very much for watching.